Keeping track of borrows at runtime with RefCell type. When creating immutable and mutable references, we use the ampersand and the ampersand mute syntax respectively. With RefCell type, we can use the borrow and borrow mutable methods, which are part of the safe API that belongs to RefCell. The borrow method returns a smart pointer to ref type, and borrow mutable returns a smart pointer to ref mutable type. Both types implement deref, so we can treat them like regular references. Make sense? So what they're stating here is that they alluded to the safe API. So a part of the safe API, RefCell has the methods borrow and borrow mutable. Borrow give you a type of ref type, which is just a reference to a smart pointer to the inner thing. And then borrow mutable returns a smart pointer to ref mutable, which is a mutable reference to whatever is inside the cell. Both of these types implement deref, which means that when you call a method on them, it's going to go into the inner type and then try the method on that. So for example, when we did borrow here, borrow didn't return a vector. Instead, it returned ref type. However, because deref was implemented on ref type, when we did .length, it went into deref and then called the length on vector. The RefCell type keeps track of how many ref types and ref mutable type smart pointers are currently active. Every time we call borrow, the RefCell increases its count of how many immutable borrows are active. When a ref type value goes out of scope, the count of immutable borrows goes down by 1. Just like the compile time borrow rules, RefCell lets us have many immutable borrows or one mutable borrow at any point in time. Okay, so here they're going over how RefCell follows the borrowing rules but at runtime. And they do it by having incremental counters that follow how many references are currently being used. Borrow increments the ref type, which is immutable, and based on the borrow rules, you can have as many immutable references currently live as you want because they're just reading. But you can only have one mutable reference at a time. And yeah, they just use borrow and borrow mutable to enforce those. Okay. If we try to violate these rules, rather than getting a compile error as we would with references, the implementation of RefCell will panic at runtime. Listing -23 shows a modification of the implementation of send in listing 15-22. We're deliberately trying to create two mutable borrows active for the same scope to illustrate that RefCell prevents us from doing this at runtime. And here's where they're doing it. So yeah, let's do that and see if it fails. See how it fails. So mock send let mutable borrow, and then push twice. So that shouldn't work. Let me just comment this out so it can just be a complete new line. Let mutable one borrow equal self dot set messages dot borrow mutable let mutable to borrow equal self dot set messages dot borrow mutable, and then one borrow dot push string from message, and then to borrow dot push string from message, And then this should fail gloriously. Cargo test. It failed. There was a panic, so you can see a backtrace. And that's about all it shows. And I guess if we wanted to know more about it, we can just read. Here it is. Oh, that opened up in the back. Let me minimize this real quick. Panicked at already borrow mutable error. So they're very explicit about it. And I got to see this message without looking at the entire backtrace, which is very nice. Okay. We create a variable oneBorrow for the refMute type smart pointer return from borrowMute. Then we create another mutable borrow in the same way in the variable toBorrow. This makes two mutable references in the same scope, which isn't allowed. When we run the test for our library, the code enlisting 15-23 will compile without any errors, but the test will fail. And this is the same error that we saw, so yes. Notice that the code panicked with the message already borrowed, borrow mute error. This is how RefCell types handle violations of the borrowing rules at runtime. Catching borrowing errors at runtime rather than compile time means that you would find a mistake in your code later in the development process, and possibly not until your code was deployed to production. Also, your code could incur a small runtime performance penalty as a result of keeping track of the borrows at runtime rather than compile time. However, using RefCell type makes it possible to write a mock object that can modify itself to keep track of the messages it has seen while you're using it in a context where only immutable values are allowed. You can use RefCell type despite its trade-offs to get more functionality than regular references provide. So what they're saying here is, well, they're noting that this is happening, the error, the panic, is happening at runtime. And some of the obvious things that means is, since it's not happening at compile time and it's happening post-compile time, it's happening later in the development process. So there's a possibility that you will find these until deployment, or hopefully like during testing you'll find these. There's also a performance hit because now the compiler is doing the checking for the reference counting at runtime. So it's not as fast as if you're using code that didn't involve this. But because we can do these things, we should note that it is allowed, it is something we can use, and it's really good for mocking out objects. So I would imagine most people use this mostly for testing. Outside of testing, they could be use cases, but I would stay away from it. Having multiple owners of mutable data by combining RefCounting type and RefCell type. Ooh, that sounds dangerous, but okay. A common way to use RefCell type is in combination with RefCounting type. Recall that RefCounting type lets you have multiple owners of some data, but it only gives immutable access to that data. If you have a RefCounting type that holds a RefCell type, you can get a value that can have multiple owners and that you can mutate. So they said this is common. I don't know how true that is, but I'll believe them. I'll take the word for it. And what's common is the combination of RefCounting with RefCell. So for RefCounting, you can only use that with immutable types that are nested within it, right? But for RefCell, it is an immutable type that allows you to mutate things. So if you wanted to, you can combine the two and then have a RefCounting, put a RefCell inside of it. So now this object can have multiple owners and they can all mutate the inner object. For example, recall the cons list example in listing 15-18, where we use RefCounting type to allow multiple lists to share ownership of another list. Because reference counting type holds only immutable values, we can't change any of the values in the list once we've created them. Let's add in RefCell type to gain the ability to change the values in the list. Listing 15-24 shows that by using a RefCell type in the cons definition, we can modify the value stored in all the lists. Yeah, okay, we can write that out. I need a main function now though. New Rust file main.rs. Function main, just so it exists. So we're using derive debug, so we can print out using debug statements, which they did here. Okay. Derive debug enum list cons, and they have it defined there, which is, I haven't imported it yet. Let me import it first. They did all the imports here. Use create list cons and null, which we haven't written yet, but we will write it. Use standard library RC use standard cell RefCell, and just finish this cons. Oh, that's where my error is. So reference counting, and then within reference counting put a ref cell, and then within that we're going to put a I32, and in the list it's still going to be just reference counting. I see. Okay. So main let value equal RC new ref cell new 5. Let A equal RC new cons, and then in cons we have RC clone, because we're cloning the value. Okay, that makes sense. Cloning the value to value, which is 5. Then RC new nil, which is the end of the list for A. Let B equal cons RC new ref cell new your value, which is 6, at least according to this. And then we're going to clone, ref counting clone A. Put a pointer to A. And we should do something similar with C. So let C equal cons reference counting new ref cell new, your value is going to be 10, and then we're going to have a ref counting clone of A, and we pass in A pointer to A. So as of right now, everything should work the same as it did before, but now we're going to be changing values. So the value borrow value is 5, right, as stated here. That is the value of A, which both of these have access to. And we're going to change it underneath all of them. So dereference value dot borrow mutable and then plus equal 10. I'm pretty sure we did a dereference first because we're like 2 out. So dereference got us into RefCell. RefCell we called the borrow mutable, and then the borrow mutable we didn't have to do anything because it's just a value. We just added 10 to it. Now see what everything looks like. Print. I'm not gonna write these out. I'll just copy and paste them. Copy. But essentially, we're just printing A, B, and C. And let's see if this compiles. Cargo run. It did. Let's make you bigger. So as we can see, it says that A, the value, is equal to 15, which is 5 plus 10 is 15. And we can see that the value in B and C have both changed to 15, which is what we wanted to see. We create a value that is an instance of refcounting RefCell i32 and store it in a variable named value so we can access it directly later. Then we create a list in A with a cond variant that holds value. We need to clone value so both A and value have ownership of the inner 5 value rather than transferring ownership from value to A or having A borrow from value. That makes sense. So what they're stating here is why they created value and then why they cloned it for A. And the reason why they cloned it is because they wanted both of them to have ownership. And because both of them have ownership over 5, or this thing, we can then just modify value like we did here. We wrap the list A in a reference counting type, so when we create list B and C, they can both refer to A, which is what we did in listing 15 as 18. So stating there is we wrap A in a reference counting type so that we can pass both A, so we can pass A to both B and C, just like we did last time, which is what we did here when we just cloned them. After we created the list in A, B, and C, we add 10 to the value in value. We do this by calling borrow mutable on value, which uses the automatic dereferencing feature we discussed in chapter 5 to dereference the reference counting to the inner RefCell value. The borrow mutable method returns a ref mutable smart pointer, and we use the dereference operator on it and change the inner value. So that is here. So like we said earlier, we use the deref operator to go from the ref counting, which is the outer part, to the inner part of RefCell. And then on RefCell, we called borrow mutable, which then gave us access to the inner value, which is 5, and then we added 10 to that. When we print A, B, and C, we can see that they all have the modified value of 15 rather than 5, which is what we saw down here, 15, 15, 15. This technique is pretty neat. By using RefCell type, we have an outwardly immutable list value, but we can use the methods on RefCell that provide access to its interior mutability so we can modify our data when we need to. The runtime checks of the borrowing rules protect us from data races, and it's sometimes worth trading a bit of speed for this flexibility in our data structure. The standard library has other types that provide interior mutability, such as cell, which is similar except that instead of giving references to the inner value, the value is copied in and out of the cell. There's also mutex type, which offers interior mutability that's safe to use across threads. We'll discuss its use in chapter 16. Check out the standard library docs for more details on the differences between these types. We have reached the end of this section, which means we've reached the end of this video. This was a lot of information. I'm happy I learned about RefCells because they allow me to mock things. And as a person that writes Python all the time, I use mocks all the time. And without mocking, I'm not exactly sure if my code works in Python. Granted, I don't necessarily have the same problems in Rust. However, taking something that's familiar to me, which is mocking, and be able to do it in Rust will make the transition easier. Thank you. Outside of that, if you enjoyed the video, hit the like button, subscribe. Peace.